Welcome to our IDQ Pro tutorial series. My name is Helena, and today I'll be talking about our Spectra Mathematics options. So to start, I've already opened a dataset. Navigate to the Spectral Analysis panel here and select Spectra Mathematics. This drop-down menu will give you a variety of options. To start, we'll select the length of spectrum. This function provides information about the length of the z dimension. For most of the data cubes, this information is independent of the region of interest, but a region of interest is still required to operate the function. Select the first spectra, and you'll be prompted with this X. Select a region of interest, and click Generate. The information will be given in the spectral plot window here. Next, we'll look at normalization. This function allows the user to normalize up to two spectra from two corresponding regions of interest. Select the first spectrum, and then select the second one. Click Generate. Both spectra will be normalized between 0 and 1. The next option is the subtraction. I'll go ahead and clear the region of interest. Subtraction subtracts two spectra from two corresponding regions of interest. So you'll select the first spectrum, then select the second, and you'll click Generate. Next, we'll look at simple ratio. This function allows the user to divide two spectra from two corresponding regions of interest. So again, select the first spectra and the second spectra, click Generate. Next, we'll look at log. This calculates the log 10 of a spectrum. Select the spectrum and click Generate. The spectrum that resulted will be log 10 of the spectrum. Next, we'll look at first derivative. This function generates the first derivative of the spectra. The first derivative of the spectrum from the region of interest is performed in two steps. First, the function averages the spectra from the region of interest, and then the algorithm performs derivation of the spectrum, converting the mean spectrum into its corresponding first derivative spectrum. So, select first spectrum, draw that region of interest, and press Generate. Next, we'll look at the second derivative. Again, you'll select the first spectrum. This function generates the second derivative of the spectra. The second derivative spectroscopy is a technique that enhances the separation of overlapping peaks. The second derivative measures the instantaneous rate of the first derivative. The sign of the second derivative tells us whether the slope of the tangent line is increasing or decreasing. And this is the resulting spectrum. Next, we'll look at low-pass Fourier transform. I'll clear my region of interest. This function performs FFT of the spectrum and removes any high-frequency data. The low-pass FFT of the spectrum from the region of interest is performed in several steps automatically after several inputs from the user. First, the function averages the spectra from the region of interest. Second, the algorithm performs a Fourier transform of the spectrum, converting the mean spectrum into its corresponding frequency domain spectrum. Third, the algorithm executes a low-pass filter with a specified user cutoff frequency. In the final step, the inverted Fourier transform algorithm is performed to generate a new dataset with only low-pass frequencies. We'll start with selecting the first spectrum. We'll click Generate, and it will prompt us with the option to enter a cutoff value. The number reflects the percent of the Nyquist frequencies in the range between 0 and 1. You can click Apply to Image, or you can click Visualize Spectrum, so you can understand what exactly is being cut off. And if you like this, then you can apply to image. And that is the resulting option. We also have the option for high pass. So I'll go ahead and X out the low pass options and clear the region of interest. I'm also choosing to reset the image at this time. Again, select the first spectrum and click Generate. You'll be offered, again, the option for the cutoff. If you visualize the spectrum here, you can see that the selected frequencies are on the other side because it's the high pass. If this is what you're looking for, then you can apply to image. If you'd like to change something, you can edit the cutoff value here. For this image, as you can see, perhaps we'll have to edit this. For the purposes of this demonstration, I will keep going. Next, we'll look at spectral correlation. This function generates comparison between two regions of interest interactively selected on the image using the spectral correlation algorithm. So I'll start by selecting the first spectrum, and then the second one, and I'm going to click the Generate button, and it gives me the value here for how correlated the objects are. The value can range between -1 to +1. A score of -1 indicates a perfect negative correlation, while a score of +1 indicates perfect positive correlation. Higher scores correspond to stronger spectral correlations. A score of 0 indicates that there's no correlation between the two areas. The next option is spectral divergence. This option generates a comparison between two regions of interest using the spectral information divergence algorithm. So to start, I will choose the first spectrum, and then the second one, the leaf and the background, and I'll click Generate. A lower score corresponds to a stronger similarity between the areas, and a value of 0 indicates that there is no divergence between the two areas. Next, we'll look at spectral angle. This function generates a comparison between two regions of interests using a spectral and angle algorithm. To start, select the first spectrum, then select the second spectrum, and click Generate. A lower score corresponds to stronger spectral similarity. A score of 0 indicates perfect similarity. Usually a score less than 0.1 radians indicates that there's no similarity. Next, we'll look at the spectral correlation or spectral cross-correlation map. This enables the user to draw a seed and cross-correlate with the rest of the image. It identifies the area of the highest and lowest correlation. It also is able to quantify the area correlated with that seed. So to start, we'll select the first spectrum and then click Generate. Another window will appear to help visualize and quantify the map pictured. Higher cross correlations correspond to a closer match between the seed and each pixel in the image. You can use the slider bar here on the histogram to visualize the image with the highest or lowest correlation. The area of the matched correlation or high cross correlation is shown in the title. Next, we'll look at the spectral divergence map. This again allows the user to select a seed, and it shows a divergence between the seed and the rest of the image. The resulting map will identify areas of the highest and lowest divergence. It also will allow the user to quantify the area correlated with the seed. So to start, you'll select the spectrum, and then you'll click Generate. And here you'll have the same option to use the slider bars here to better visualize. Lower divergence corresponds to a closer match between the seed and each pixel in the image. The total area of the matched divergence, or lowest values, is shown in the title. Next, we'll look at the spectral angle map. You'll start by selecting the first spectrum and clicking Generate. This measures the spectral similarity between the spectra of each pixel in the hyperspectral data and the specified reference spectra or the seed by using the spectral angle mapper classification algorithm. A lower score corresponds to stronger similarity. A score of 0 indicates perfect similarity. Usually a score less than 0.1 indicates that there's no similarity between the pixels. A static similarity threshold will have to be applied to recognize similar and dissimilar areas. So the user can select the seed, as I've already done, and then it shows a spectral angle map between the seed and the rest of the image. It indicates the area of highest and lowest angles and identifies the area correlated with the seed. The mapper has the 3 panels: the spectrum of the seed, which shows the average spectra across the selected seed area, the histogram of the image, where each value is a spectral angle score, and the monochromatic image of the map, where each pixel is a spectral angle score. You can use the slider on the histogram to set a threshold value to visualize the images with the highest or lowest similarity. The total area of similar objects with the threshold defined is shown in the title above on the map. Next, we'll look at the Savitzky Golay smoothing option. The Savitzky Golay smooths noisy signal data using a least squares digital polynomial filter. It optimizes and visualizes the performance of the smoothing algorithm on an individual spectrum from the selected region of interest. So to start, you'll select the spectrum and click Generate. You'll be prompted with the polynomial order and the frame size. The polynomial order corresponds to the degree of the polynomial fitted to the points in the moving frame. The default value is 2. Polynomial order values must be smaller than the frame size if the frame size is a positive integer. The default value is 10. Now the frame size modifies the frame size for the smoothing function. If the frame size value is greater than 1, the rolling window is the size of the input number and independent of the number of bands and channels. Higher values smooth the signal more with an increase in computational time. If the frame size is less than 1, the window size is a fraction of the number of points in the total number of channels. For example, if the frame size value is 0.05, the window size is equal to 5% of the number of points in the total number of channels. When the process is complete, the new spectrum will replace the original image. We suggest clearing the spectrum by pressing Clear before drawing a new area of interest. And that goes through all the options for our Spectral Mathematics panel.